we have talked about some of the basic signals and some of the basic operations that we can apply on signals. Now let's try a few examples, and those examples are going to use the functions that we have written so far. So here is a set of examples. Let's work on them and one by one. So let's start on working on this particular one first, right? And this is xn is a composite signal made up by two impulse sequences. This impulse sequence, which is centered at n equals to -2, and this impulse sequence, which is centered at n equals to 4 actually. So and n goes from like -5 to 5. So let's try to construct this composite signal xn by using uh, the impulse sequence function that we have written before, this particular function, right? And so I'm gonna clear up my workspace, and because we're gonna sort of work on every example, so let's write a script. Let's write a script instead of typing in the command window. So I'm gonna so let me check my path. Yes, I think I'm at the correct path. So I'm gonna write a script. Let's call it scrpt1 script, just s1.m, script1.m. And then now let's try to write this signal. So the first thing I'm gonna do is to write the construct the horizontal axis. So it's gonna go from -5 to 5 with a stride of 1. So that's our horizontal axis. Now let's construct xn. So the thing that I'm gonna do is that I'll just type the command, and then I'll explain what the command actually means. So 2 times impseq, that's the function that I have written before, impseq. And then it's n plus 2. So for this particular function, the peak is going to be at n equals to -2. So that's going to be the first input. And then the range of horizontal axis goes from -5 to 5. So that's the first call to impseq. And then subtract. I'm calling impulse sequence function again. And for this impulse sequence, the peak is at n equals to 4. And then the range is still from -5 to 5. And then that's it. That's our composite sequence X. One of the things that might be puzzling is this particular call. If we go back to look at the definition of the function, it actually returns two output variables, both the signal's amplitude x and also the horizontal axis n. But here we are actually using the output inside of an expression. So we are actually using 2 times to multiply the output of the impulse sequence, and then subtract the output of another impulse sequence, which is centered at 4. So in fact, Matlab actually uses only the first output. If you actually use the function in an expression, it's going to use actually just the first output of this particular function. So if you don't believe me, you can just copy and paste this into the command line, and then we're going to see what's let's just copy it, and then let's just paste it into the command line. Here I'm actually not assigning the output to any variables. So let's just run it, and then it's gonna just give you one sequence, and this sequence happens to be the first output, which is x, right? It's not really giving you two outputs. If you want the second output, you have to explicitly assign it to a output variable. So if you do this, so you're gonna get x. That's exactly the same here, and then you're gonna get n. So if you are using this function inside of an expression, it's only the first output of this particular function are going to be effective inside of this expression. So effectively, you're actually multiplying the x output, the first output of this function, with 2, which is a vector multiplied scalar, and then subtract the first output of this call, and it's going to be the x. of this, the x output of this particular function. So that's going to be our x signal, but let's take a look at it. Let's make a plot of it. But this time I'm going to use a subplot. Because we have a 1, 2, 3, 4. We have 4 examples, 4 exercises for this example 1. We're going to do a subplot. I'm going to do a 2-row, 2-column subplot, and then I'm going to plot in the first subwindow, and then I'm going to do stem nx, and then I'm going to give it a title, sequence in example 1a, say. Misspell the title. And then x label. I'm going to label the x-axis just as n. And then y label. Y label is just going to be xn. This might be easier to understand. And then let's just run it. You can just run this script by click on this run button. Now it's supposed to make a plot. So that's the plot. That's the plot. We're seeing a spike at n equals to -2, and this spike has an amplitude of 2 because you have multiplied 2 here. And then another spike at n equals to 4 here, and it has an amplitude of -1. Right? That's our first example. Now let's look at the second example. This example is so n goes from 0 to 20. That's the range, and then it's n times u is the unit step function, unit step sequence. So it's basically un subtract 10, and then multiply with n. It's basically a dot multiply. And then this is an exponential sequence. Right? And then another unit step function subtract another unit step function, multiply inside of the square bracket, right? And let's start a new section. And this time we're gonna use the unit step function, or step seq function that we have written so far. The step seq here. That's the function. So the first thing I'm gonna do is still try to sort of define the range of the horizontal axis. So n goes from like a 0 to 20. That's it. So x, I'm gonna call it what am I gonna call it? So what I'm gonna do is that I'm gonna define a intermediate value, intermediate sequence for holding this expression first, and then another intermediate sequence for holding this particular sequence, and then I'm gonna add them together. So the first intermediate sequence I'm gonna call it x1, which should be just the expression for this particular selection. So I'm gonna call it x1, and x1 equals to n dot multiply. And dot multiply, that's n multiply this thing. So it's a element-wise multiplication. And inside of this multiplication, I have to call step seq. And the first call to step seq has a switch location n equals to 0. So it goes from 0, and then the range is 0 to 20. That's the first call to step seq. And then I'm gonna subtract it with step seq. This one has a switch location at 10, and then the range is still 0 to 20. So that's gonna be my first sequence. Make sure the parentheses are paired. Right. That's my first sequence. Now let's construct the second part of this sequence. Let's just call it x2. x2 equals to what? x2 equals to 10 times exp minus 0.03 times and subtract 10. Right. And then that's basically this part of the expression, right? And then I'm gonna do another dot multiply with with these two step functions, but I'm including them inside of this parenthesis. So step seq again. So the switch location for the first one is from 10 at 10, and then the range from 0 to 20. Subtract step seq. The second one is 20, and then 0 to 20. So that's my x2. That's the x2 basically. Right. And then now let's try to construct the final sequence, which is x. So x equals to x1 plus x2 basically. Right. The reason that I'm just using the plus sign here, and also the dot multiply here, is because the range for all the sequences that's being involved are identical. So I was not using the sig add or sig mult, those functions that I have written by myself. So but in future examples I'm going to show you how to use those functions, right? But here it's just because the range is identical, so we don't really need to use those functions. Now let's make a plot of this x sequence. Still I'm going to use subplot, but this time I'm going to plot in the second subplot, and then I'm going to do stem and x, right? So if you want to sort of execute just this portion or this section of the codes, what you can do is hold down the control key and then press enter. Or what you can do is to right click in this particular section, the highlighted section, and then select evaluate current section. And it's also showing you a shortcut, which is control plus enter. Hold down the control key and then press enter. So let's just run this particular section. And then let's take a look at the figure. So that's going to be my second signal x. Right. So you can sort of imagine where this kind of slope actually coming from, right? This slope actually is coming from this n multiply these two. So n actually keeps increasing, right? Keeps increasing from 0 to 20. And un is a unit step function. So these two unit step functions subtracting each other actually gives you a boxcar, right? The switch location from 0 to 1 for this function is at 0. So at location 0, it's going to switch to 1, from 0 to 1. And then this one is actually has a switch point at 10. So at location 10, it switches from 0 to 10 to 1. So these two functions subtracting each other, it's going to give you a boxcar that has a unit amplitude from 0 to 10, right? And then it has 0 amplitude after 10. Right, so that's if you multiply this boxcar with this n, that's gonna give you this half of the signal. You see, it's gonna give you this half of the signal because it's basically n, this linear function multiplying a boxcar. And then you have this exponential function, but it's an exponentially decaying function because the amplitude here is actually negative. So it's actually decaying with n. And then this is another boxcar actually, because this one actually switched from 0 to 10 0 to 1 at location 10, right? This one switches from 0 to 1 at location 20. So subtracting them actually gives you a boxcar that has unit amplitude from 10 to 20. From 10 to 20. You use this boxcar to multiply with this exponentially decay function that will give you this half of the signal. So that's why the signal looks like this, right? Of course, you can also try to decorate it by give it a title. Let's just give it a title. Sequence in example 1b, for example, right? And then x label, n, y label, x, n. That's it, right? So now you get some labels. Now let's look at the third example, right? The third example. So for this example, it's gonna use some random sequence. It's gonna use some random sequence. It's basically a cosine function plus 0.2 times Wn. Wn is a Gaussian random sequence with zero mean and unit variance. And Matlab actually has a special function for generating this kind of a random sequence. It's called a rand n. It's called rand n. Rand n. And you can sort of take a look at its explanation or its help page. Normally distributed pseudo-random numbers, right? It's a normally distributed, which means that it has a mean of 0. That's exactly what we want. Unit variance no, normally distributed has unit variance, so that's exactly what we want, right? So let's try to write this particular sequence. Again, the first thing I'm going to do is to define the range of the horizontal axis. So n goes from 0 to 50. N goes from 0 to 50. And then let's try to write the x function. So x equals to cosine 0.04 times pi times n. So this kind of intrinsic function is going to be applied element-wise. N is a vector. Cosine function is going to apply element-wise to this particular vector. It's basically 0.04 times pi times this n vector, right? And then I'm going to add 0.2 times rand n. And for this rand n function, I'm going to use an input which is the output of the size function of n. So whatever is the size of for the horizontal axis, this size function is going to output the rows and column numbers of this n vector, and then that output is going to be used as the input to the rand n function. And then the random n function is going to generate a random Gaussian random sequence, normally distributed Gaussian random sequence with exactly the same size as the horizontal axis n. And that's it. That's it. And let's try to make a plot of it. Subplot 2, 2, 3 now. It's the third subplot, right? And then let's just stem and x, and then give it a title. Basically, I should just basically copy over. We'll see. And then let's just run it. So that's gonna be our third sequence, and you can sort of see, on average, it has some kind of cosine shape, right? But the amplitude is like not exactly following the trend. It oscillates up and down. That's because of the effect of the Gaussian random number that we're actually adding to the cosine function, right? Now let's try the last one. That's the last one, last example, which is basically a sequence that's actually repeating itself. Right, 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. It's a periodic sequence. It's a periodic sequence with a period of 1, 2, 3, 4, 5. The period is 5, or fundamental period is actually 5. So let's see how we can actually construct this this particular sequence, right? So this time I'm gonna sort of use something that's slightly more complicated. And first thing I'm gonna do is still to define n goes from like -10 to 9, -10 to 9. Now let's do some. Let's first define the one period, just a single period of this periodic sequence, right? Which is basically 5, 4, 3, 2, 1. So I'm gonna just try to. I'm gonna type x 5, 4, 3, 2, 1. Right, that's just the one period of this periodic sequence. At this point, there are multiple ways of doing this kind of thing, but I'm gonna use a method that's gonna be slightly more interesting. I'm going to define a new variable, a new sequence. Let's just call it um, x tilde or tilde. I'm going to call it x, and I'm going to use x prime times ones. Ones. Ones, it's going to have one row and 4 columns. So if you guys want to see what actually is going on, it's a so x here is a row vector, right? By transposing it, I'm getting a column vector. So x transpose is a column vector. It has just a 1, 2, 3, 4, 5. It has just five rows and one column, x prime, right? X prime. And then I'm doing a multiply. It's not a dot multiply, you see. It's a multiply. So without the dot declaration, multiply actually means matrix. It's a linear algebra multiplication. And then multiply with what? A sequence of ones. A sequence of ones. And this sequence of ones has one row and 4 columns. So here it's a 5 row, 1 column times 1 row, 4 column, right? So can you guys imagine what's actually going to be x tilde, right? But that's not exactly what we want yet. X tilde here is going to be 5 rows, 4 columns actually. It's going to be a matrix of 5 rows and 4 columns. But that's not exactly what we wanted. We want a 1 row sequence that's kind of repeating itself. So the next thing I'm going to do is to transform it a little bit. X tilde equals to x tilde colon. So here I'm actually converting a matrix to a vector. And this vector is going to be a column vector. So what I want is a row vector. So again, I'm going to transpose it, but I'm enclosing the whole expression inside of the parentheses before transposing it. So that's going to be x tilde. That's going to be what we want, right? And then if I want to make a plot, and then stem and x, and so let's look at the result, see if it is what we wanted. It looks like I have an error using stem. So it's saying, oh, it's not x, it's x tilde. X tilde. That's now let's look at what's actually the output. Right, that's the output from -10 to 9. Right, and then it's periodic. It's periodic, repeating itself. Right, that's exactly what we wanted. But now let's sort of take a careful look at some of the lines. So here what I'm saying is that the x tilde is going to be 5 rows, 4 columns, and let's see if that's true, right? So here x equals to so what's actually x? X 5, 4, 3, 2, 1, and then x prime times 1s, 1, 4. It's giving you a matrix because of what I was telling you. This is the linear algebra multiplication. It's not a element-wise multiplication. And this x prime is actually, if you look at the size of x prime, 5 rows, 1 column, right? And then if you look at the size of 1s, 1, 4, it's actually 1 row, 4 column. So linear algebra multiplication of these two matrices is going to give you another matrix that's 5 rows, 4 columns. That's 5 rows, 1, 2, 3, 4, 5. 5 rows, 4 columns. 1, 2, 3, 4, 4 columns, right? And if you actually, and then at this line, I'm actually flattening this matrix into like a 1 column vector. So if you do x tilde, so here, let me just repeat this command. Evaluate selection here. And then x tilde is this 5 row 4 column matrix. And x tilde colon, it's going to flatten it into a column vector. You see? That's the effect of just a column without any kind of range index, right? And then if you transpose it, it's going to be a row vector, and that's our output. That's the output we want, x tilde. I'm assigning the output back to x tilde again. So I'm reusing the same variable to store this transposed row vector actually. So, and then I'm making a plot. So that's how you can actually use how you can actually construct a periodic sequence. All right, that's one of the ways. One of the ways. Of course, there are multiple ways, right? For example, by using repmat, right? Do you guys still remember repmat? By using repmat, you can also construct the same sequence, right? It might be also easier to use repmat. You can sort of see repmat. I'm basically just repeating x by like 4 times, uh, one time in the row and then 4 times in the column, I think, right? 4 times in the column. 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, right? 4 times in the column. Is that the figure actually? 1, 2, 3, 4, 4. It's just repeating it by like 4 times. So refmat x14 is all it takes to actually generate this periodic sequence, right? That's another approach. That's another approach to do this. So all I have to do is to comment out these 2 lines, comment, and then replace them with x tilde equals to repmat x14, right? And then it should give you exactly the same result. Let's just run it. Right, exactly the same result. Right. And you can also think of other ways, maybe using an outer product of vectors, that kind of thing. So that's example one. That's example one. Now let's work on example two. Some additional examples here. First, we're going to construct a sequence, and then we're going to compute and also plot these 2 functions, right? And you can sort of see these 2 functions actually involve shifting operators. This is shifting by 5. This is shifting by like -4, right? This is shifting by like a 3, but there's a folding operation involved in it, right? Because you can sort of see it's not n subtract something, it's something subtract n. So the sign in front of n actually has changed. So basically it's a folding operation, right? There's a folding operation involved. And there's also a shifting operation, because if you just fold without shifting it, you won't get this 3, right? So let's see how we can actually implement these 2 sequences. Again, I'm going to work in the same script, script 1. Write a new section, right? So what's going to be the horizontal axis for our example, right? What's going to be the horizontal axis? It doesn't really matter too much. It doesn't really matter too much for defining this particular sequence. For defining the horizontal axis for this particular sequence, it doesn't really matter too much. So you can actually use any kind of a starting and ending value. Doesn't really matter, because all the functions, for example, sig shift, that kind of thing, sig mult, that kind of thing, is gonna automatically take care of the alignment of the horizontal axis for all the input signals for us. So here we can just use an arbitrary input horizontal axis. Let's just call it n goes from like a let's say -2 -2 to 10, for example, -2 to 10, and then x is gonna equal to what? X is gonna equal to, so it goes from like 1 to 7, and then reduce it from 6 to 1. So what's gonna be our x? Our x is gonna go from like 1 to 7, 1 to 7 with a stride of 1, and then 6 with a stride of -1, and then down to like 1, right? So that's gonna be our x signal. That's gonna be our x signal. So let's gonna this time we're gonna construct this particular sequence in multiple steps. So we're gonna first generate a signal that's being shifted, and then another signal that's also being shifted, and then we're gonna add these 2 signals, subtract these 2 signals. So first let's construct this signal, right? to construct this signal is relatively simple. All we have to do is to sort of call the sig shift function. So how do we actually call the x shift? We're going to call the sig shift function, and then the sig shift function is going to have two outputs, and this time we're going to need both outputs, actually, both the amplitude and also the horizontal axis, because after shifting it, after shifting the original signal, the range is going to change. The range of non-zero numbers, non-zero signal amplitudes is going to change. So we are going to need the second output. So let's define two output variables, x11 and n11, equal to sig shift xn, and then we're going to shift it by a unit of 5, right? So that's sort of the last input, sig shift. So that's going to be x11 and n11, x11 and n11. And then we're going to need another signal that's being shifted. Let's call it let's call the output x12 and n12 equals to sig shift xn, but this time it's xn plus 4. N plus 4 means that the amount of the shift is actually minus 4 here, right? So that's sort of the amount of the shift. Okay. So once we have these two elementary functions, we can use sig add to actually add these two numbers, two sequences together. But don't forget, the horizontal range is going to be different. So n11 and n12 are going to be different this time. So we have to use sig add to add those two sequences together. So how do we call this function, right? We're going to call this function with two outputs. Let's just call it x1 n1 equals to sig add. Sig add requires 4 inputs: the amplitude of the first signal, right, and then the horizontal axis of the first signal, and then the amplitude of the second signal, and then the horizontal axis of the second signal. So the amplitude of the first signal is going to be 2 times x11, and the horizontal axis of the first signal is just n11. And then the amplitude of the second signal is minus 3 times, because we are using sig add, it's addition. So minus 3, we have to account for this minus sign by using this coefficient, minus 3. Minus 3 times x12, and then horizontal n12. Right? That's going to be our output. That's going to be our output. Right? And if we want to sort of take a look at this particular sequence, we can do another subplot. Let's just do two rows, 1 column, and then we're gonna make plotting the first subplot, and then do stem n1 x1, right? And then let's do the title seq enc in example 2a x label label n, and then y label let's call it x1n, right? And then let's give it a try, see if it's gonna generate any mistakes. So that's gonna be our first function, I think, right? It's gonna be our first function. Maybe I should clear out this figure first, CLF. Clear out this figure first, and then rerun the script, this section. Control Enter, and then it's gonna generate the output. And you can sort of see the range is actually quite different from our input range, right? The range actually goes from like a minus 6 to positive 15, I think, right? If we here, if we actually do a let's just do a access tight. By doing access tight, it's gonna sort of make the access tighter right around the location where you have amplitudes, right? So it goes from like minus 6 to positive 15, I think, right? That's our first sequence. Of course, you can plot all the intermediate results, right? So this maybe what you want to do, maybe what we want to do is to do a stem, for example, nx, right? That's our input signal. That's the x signal itself. Goes from like 1 to 7 and then reduced to 1. Goes to like 1 to 7 and then reduced to 1, right? And then x11 and then x11 n11 is going to be the first shifted signal, right? So if we want to sort of look at the shifted signal, let's hold on to the old plot and then stem n11 x11, that's plotted in black. That's sort of the shifted signal. It's being shifted to the right by a unit of 5, I think, right? So minus 2 becomes positive 3, so a shift of 5 units to the right, right, to the right. And then let's stem n12 x12, I think, is it n12 x12? That's this shifted signal. That's this shifted signal. So n12 x12, let's use red, right? So that's being shifted to the left by 4 units, right? So it's 10 becomes 6, so shifted by 4 units, right? So basically that actually defines the range of the output signal. Do you see? So if you try to add the red signal to the black signal, then the result is gonna range from like minus 6 to positive 15. That's exactly the output range, right? That's exactly the range of the output signal. But the thing is that there is a coefficient of 2 on the black signal, I think, and then a coefficient of minus 3 on the red signal, right? You have to multiply the red signal with minus 3 and then add it to 2 times the black signal, and then that's going to be our result. That's stem n1 x1, but this time let's use a different colors. Let's use green, for example, right? That's our output sequence. If you do access tight, right. Okay. So this is basically a demonstration about seek shift and seek add, right? We have made some sort of quite complicated sequence. Now let's look at the second one. The second one, slightly more complicated for this particular sequence because it involves both a shift and also a fold. So let's see how we can actually deal with that. See how we can deal with that. Right. So let's still go back to our script. Write a new section. Because I'm gonna still use this the definition here, n and x. So I don't want to sort of retype n and x anymore. So there's no need to do that. But I'm gonna define some new variables. So what I'm gonna do is that I'm gonna sort of try to construct this signal first. What I was telling you that it involves both a shift and also a fold, right? So which operation that we should apply first? Let's give it a try. Let's try to fold it first, right? Let's try to fold it first. Fold it. If you fold it first, then it's gonna generate x minus n basically. If we want to generate x minus n, all we have to do is to call seek fold. Let's put the output into x21 and n21. n21 equals to seek fold, basically xn. That's it. All right. Now let's consider the shift. So x21 and n21 is going to be a signal that's kind of a folded version of x. So it's basically x minus n. So now what's going to be the amount of the shift? Is it positive 3 or is it negative 3? Right. Don't forget, what we want is to shift x. Now we have to shift x minus n, right? Shifting x minus n means that so let's try to generate another signal x21 n21. I'm gonna reuse the variable. So seek shift x21 n21. But now we have to determine if it is a positive shift or a negative shift, right? Um, so if you think about it, the x3 minus 1 actually equals to x minus n. So if I try to type it here, so x3 subtract n equals to what? X minus n subtract 3 actually. Isn't that right? So if you actually put the minus sign into the parentheses, it's minus n and then positive 3, right? So it's actually minus n subtract 3. So basically what you want to shift is a positive unit of 3. It's not minus 3, it's positive 3 actually. Because if you look at the stuff that's inside of here, it's n subtract 3, right? So the amount of shift is actually positive 3. And then I'm going to use x21, n21 as the input. And then the output is still going to be assigned back to x21, n21. So I'm basically reusing the same variable names. So I think that accounts for both the fold and also the shift, right? And then let's try to construct the second one, which is basically shifting the signal by 2, right? Let's call it x22 n22 equals to sig shift x n and then 2, shifting signal by 2. And then basically uh, that's uh, that's the second shifted signal, right? And then we have to sort of do a multiplication. This time I'm gonna use the sigma out because certainly the range of these two signals are actually different. So let's use sigma out to multiply them together, right? So basically I have to multiply this shifted signal, basically x22, with x itself. So let's use the sigma out. So it's gonna be sigma out. First signal is gonna be x n, and then the next one is x22 n22, right? But what's gonna be the output, right? Again, let's still try to reuse some of the variables. I'm gonna assign the output back to x22 n22, right? Right. Okay. So x22 n22 now contains the multiplication of these two signals, right? So the next thing that we're gonna do is to add these two signals together, right? So basically we'll have to add x21 with x22 and accounting for the differences in the range of the horizontal axis. So in order to do that, we're going to use sig shift. So x2 n2 sig add. Let's use sig add. It's going to be x21 n21 and then x22 n22, right? So that's it. That's that's uh, that's um, that's the final result, right? And then of course you can sort of make a plot of it. 2 1 this time I'm going to use the second as a plot, right? And then stem n2 x2. Of course we can copy and paste to B, and then the vertical axis is like x2, right? Let's just run it. So now that's our output sequence. You guys can sort of imagine how this output sequence was constructed by composing all those different elementary signals and all those different kind of signal operations, right? So that's our second example, right? One of the questions that you can sort of think about is that is there a second way for constructing this thing? Here I'm actually doing the folding first and then doing the shifting. But can I do the shift first and then do the folding? Right? Of course you can. You can try to do the shift first and then do the folding. Of course. Um, But if you try to do that, what's going to be the amount of the shift? Is it going to be positive 3 or negative 3, right? And that's one of the questions um, you guys can find out by yourself by doing some simple experiments, right? Now let's work on example 3, right? And example 3 is actually a complex sequence. You can sort of see here. It's minus 0.1 plus 0.3j times n. N goes from like minus 10 to 10. And this is sort of the complex exponent of this exponential function. So it's an exponential function, a complex exponential function. What we have to do is to plot its magnitude, the magnitude of the entire sequence, the phase of the entire sequence, and also the real part and imaginary part of the four, in like 4 different plots. So first, let's go back to this figure window and clear out the figure window, and then let's go back to the editor window and work on this particular sequence, this complex sequence, right? So let's first try to construct this sequence first. The sequence is not too difficult to construct, but if we want to sort of plot all the different information about this particular sequence, we're going to need some additional Matlab functions. So how are we going to construct this sequence, right? So first thing, we're going to define the range. So n goes from minus 10 to 10 with a stride of 1, right? And then let's do x. So to construct x, let's define this thing here, right? Let's just introduce a new variable. Let's call it alpha. And then alpha, it's a complex number, and equals to minus 0.1 plus 0.3 I. We can use either I or j, right? In Matlab, either I or j followed by a number, by a floating point number without any kind of operator separating the number and the j, means that this is the imaginary part. The whole thing is the imaginary part, right? And then that's going to be our alpha. And then what's going to be our x, right? So x equals to exp, because it's exponential function, right? And alpha times n. So alpha is a complex number, but it's still a scalar. It's just a number, right? And then just multiply with n. And that's gonna be our sequence x, and x is gonna be a complex sequence this time because alpha is a complex number times a real horizontal axis that's n, right? But now let's look at how we're gonna make the plots. So the simplest part is actually the real part and the imaginary part. We can extract the real part and imaginary part by just using Matlab function real and imag. So that's relatively easy. So let's try to make these two plots first. So I'm gonna do a subplot with 2 rows, 2 columns, and I'm gonna use the first subplot, and then I'm gonna plot the real part of x, and then the horizontal axis is just n real x, and that's gonna be the real part. And let's try to give it a title. Right, and then maybe x label. That's the real part. Maybe let's just put it on one line to make it easier to identify. And then subplot 2 row 2 column, and then second plot I'm gonna plot the imaginary part by using the imag or imag function. Title imaginary part, and then x label still n. And then third subplot, so use 2 row 2 column third subplot. But this time what's gonna be the stuff that we're gonna plot? It's gonna be the magnitude. Let's try to plot the magnitude. And the magnitude is basically the absolute value of the complex numbers. It's a complex number sequence, so it's a vector of complex numbers, right? And the ABS function, that's sort of the intrinsic function of Matlab, is going to take the length. It's going to be applied element-wise to the x vector, and it's going to compute the length of each of the complex number inside of this x sequence, right? And then we're just making a plot of it. and then title the magnitude. Just call it magnitude. And then the phase. What's gonna be the phase, right? What's gonna be the phase? You guys can sort of imagine what's gonna be the phase. It's pretty much 0.3 times n. That's the phase, right? But the Matlab actually has a uh, also has an intrinsic function, and this intrinsic function is called angle. So if you type help angle, it's gonna tell you what this function is for. It's telling you it's called phase angle. So angle h is gonna return the phase angles in radians of a matrix with complex elements, right? And our input is gonna be the x sequence. It's a vector. It's a row vector of complex numbers, right? And the angle is gonna compute the so-called phase angle. The so-called phase angle of each of the complex elements inside of this row vector, right? And it's actually in terms of the radian. The result is going to be returned as radian, in terms of radian. So if you want to convert it into a degree or angle in terms of degree, then what you have to do is to multiply with 180 and then divide by pi. So that's what we are going to do here. So subplot 2 2. This time it's the 4 subplot. Stem n, right? And then we're going to call the angle function on x, and then the result is going to multiply with, we're going to multiply the result with 180 degrees divided by pi. That's sort of the coefficient that I have to use in order to convert a radian to a degree. So basically here we are actually converting the phase angles from radian to a degree angle, right? And then we're going to call it title, that's phase. And then let's just run it. Let's see what's going to be the result. Right. So here is the real part, right? The real part, and then that's the imaginary part, and then the magnitude. So if you look at the expression, the magnitude is going to be e to the minus 0.1, basically. Minus 0.1 times n, basically. It's e minus 0.1 times n, right? So because the coefficient, so n goes from like minus 10 to 10, but the coefficient is minus 0.1, so it's going to be a decay sequence. The amplitude is going to decrease. The magnitude is going to decrease with n. N goes from minus 10 to 10, but the amplitude actually decreases. Right? So it's going to decrease from what value? From e to the minus 0.1 times 10, basically. Right? So what's actually the value of e to the, so exp minus 0.1 times minus 10 times minus 10 times minus 10. So it's about 2.7183. So that's going to be the length of the first stick here. It's a little bit short of 3, but it's 2.7 something. So it looks like the magnitude is right for the first point, right? And then for the last point, it's what? For the last point, it's a minus 0.1 times positive 10. Then it's going to be minus point exp minus 1 actually, right? So it's going to be 0.3679. So it's less than 1, definitely. It's less than 1, right? It's definitely less than 1. It's 0.367. It's close to 0.4. So it's close to 0.4. The magnitude looks right, right? Looks right. It goes from like the correct value to about the correct value. And then what's going to be the phase angle? It's going to be, in fact, it's going to be e to the 0.3 times n j. So what's going to be the phase angle? It's basically 0.3 times n, right? 0.3 times n, and the n goes from like minus 10 to 10. So the phase angle in radian, it's pretty much minus 3 to positive 3, I think. Minus 3 to 0.3, positive 3. So the phase angle. minus 3, if you minus 3 convert it into degrees, that's multiply 180 divided by pi, right? So about 171.8, 172 degrees. So it's a little bit short of minus 200 degrees. And then increase it to positive 3. So positive 3 is like a positive 172 degrees, right? So 172 degrees. So it's about right, actually, right? It's about right. Should be right. Should be right if the codes are correct. So that's how you can actually construct a complex sequence and look at all the kind of different information. So basically, all those things actually quantify a complex sequence. You can sort of determine a complex sequence uniquely by either using its real and imaginary parts or by using the magnitude and the phase angle information. So these two these two information uniquely determines a complex sequence, right? These two also uniquely determines a complex sequence, right? So, and if you know this one, if you know the real and imaginary part, you can sort of figure out what's going to be the magnitude and the phase. And on the other side, if you know the magnitude and the phase, you can also infer what's going to be the real part and the imaginary part, right? So those information are kind of not unique, and you can sort of compute one kind of information from the other kind of information.